we're looking at a concept called as equipotential surface. So let me do this first. So we remember this, right? So we are looking at a positive charge, and these are not so well drawn electrical field lines. There are new set of lines over here, this blue set of lines, right? Blue dotted lines. So what can we tell you about it? Well, they have a common center, they're concentric. Okay, what else can we tell? They are at equal distance in some sense. What else? Anything to do with electrical field you guys can think of? Let me give you guys one more clue. Now, we are looking at a test charge and a source charge, right? Source charge and test charge. Now let it make it go round the source charge. So what is happening? What's happening? What is changing and what is fixed? Of course, the position is changing. The force in the direction of force will be changing, right? You can see the direction of force will be changing. What else? But the magnitude of force remains the same. Is it not? Can you see that? Magnitude of force on the test charge remains the same. Of course, if I change the radius or the distance away or I make it near, the magnitude is different. But if I make it go round around this point charge, the magnitude of force remains the same, but the direction keeps changing. And that's what we have represented over here. At all of these points, the magnitude of the force will remain the same. And all of these points, the magnitude of force will remain the same. And remember this 3-dimension, right? This is a space. So this is 3-dimension. So it can be a 2-dimensional stuff also or a single dimension stuff also, depending on what kind of charge we are talking about. Remember, this is an idea. This is only for your point charge, but for different scenarios like dipole or say two plates and all of that, like I have drawn over here actually. So things will be different. It can be 2-dimension, single dimension, so on and so forth. So we can have something called as equipotential line, equipotential surface, so on and so forth. Okay guys, so what is this? The name itself tells equipotential, equal potential. So this is an imaginary surface, a plane, a line where the potential, electrical potential remains the same. It's like the contour line on a map which we saw, but for electrical field. So all the points on the surface have the same amount of electrical potential energy, basically. For example, these are two plates and we already seen this. The field lines go from positive to negative. And this is a finite scenario. So the field line will kind of bend over here, right? If you guys remember, it'll bend a bit. Of course, here we have field lines coming in, so on and so forth. There are quite a few things happening over here. Now, if I take up certain distance away from the plates, actually it will be something like this. And there's a bending and all of that. So basically, this set of plane, again, this is 2-dimension. You have to imagine it to be in 3-dimension space, and this is a surface. So all of this surface, in this case, we are just looking at a line. All of this set of, if you pick up any point on the surface, the potential will be, electrical potential will be same. If I pick up any of this set of points, the potential will be same. Any of this set of points, the potential will be same. Right? And that space and that surface is your electrical potential surface, as simple as that. An equipotential surface is a surface, real or imaginary, where all points have the same electrical potential. This means that no work is required to move a charge from one point to another on the surface. This is another way of communicating. Right, because they are equipotential, the amount of work that we need to do on the charge to move along the surface will be 0. So let us end with an example. So the same funda, we have two plates, finite plates, and from the positive end, say this is at 120 volt, and say, of course, this is at 0 volt, right? So this set of lines or plane will have 90 volt. This set of plane or points on this plane will have 60 volt, 30 volt, and 0 volt. And the field lines will be perpendicular to the surface, if you guys can observe, right? They're perpendicular. If I pick up any point over here, say here and here, A and B, and if I move a charge from A to B, potential difference will be shunya. Okay, guys. Because the reason being they're equipotential. That's the whole funda. Right? It's very simple idea. So you guys can pause and have a look.